Okay, welcome back, everybody. Okay, so today I'm going to finish talking about the Lorentz system, and we're going to go a little bit more into depth on what it means for the system to be chaotic. So we're going to get into this notion of uncertainty in initial conditions and chaos in ODEs. Before we do that, I want to just briefly talk about the homework. I think some of you have been maybe struggling on a couple of these problems, making them a little bit more difficult than I intended for them to be. So you'll notice that this homework, we're starting to kind of explore ideas that were touched upon a little bit in class, but I really want you to go beyond what I demonstrated in class. So I'm just going to kind of start this example of computing a matrix that does the derivative of a vector f. How many of you are still working on this problem or having some trouble with it? How many of you have this matrix and know what the answer is? Okay, maybe I'll just go really quickly because all of you seem to have it. Right, so I've had a lot of questions about whether or not we're supposed to do this for like general data or specific numbers in Matlab. Like, are you supposed to code something up in Matlab? And the answer is no. I literally just want kind of a by-hand mathematical expression for if you had these data points, F1, F2, F3, F4, I'm only going to do 4, and you wanted to use those to compute the derivatives, at time 1, time 2, time 3, time 4, you can do that by multiplying with a matrix. Okay, so what is, based on our finite difference derivative, what is the forward difference F1 prime? Right, F2 minus F1 divided by delta x or delta t. Is it a function of t or x? T? As a function of delta t. So all you have to do is find this row vector here just has to reproduce this expression. So I have a 1 over delta t times F2. I have a minus 1 over delta t times F1. And I have 0 F3s or F4s. Okay, pretty simple. So that'll give you the first row. For the second and third and the middle rows, you do central difference. And for the last row, you do a backward difference. Okay, that's all I'm asking for. So like no MATLAB code needed or anything fancy. Are there any other big questions on the homework? Yeah. Sorry, x dot equals that matrix times x. Apologies, that's a typo. Yeah. Okay. Yeah.
On that last problem, when you're calling, or at least the first part, you basically just write your equation, the ducking that you outlined in the homework, and then just call it equal.
Yeah.
Okay.
Yeah, so for the last problem, we're simulating this duffing problem, this duffing example with a bunch of parameters. I think it's like alpha, beta, gamma, omega, delta, right? A ton of parameters. So this is actually a lot like the Lorentz system we did in class, where I'm going to define a general right-hand side vector field, and then I'm going to kind of lock into place those parameters using ODE 45 and function handles. You could hard code it. That would be like one way to do it, but it's a little less flexible. Okay, good. So today we're going to talk more about chaos in the Lorentz system, and then on Monday we're going to talk about chaos in more general physical systems like mechanical linkages and astrophysics problems and fluid dynamics. So Monday will be more of an applied lecture, a little less mathematical, which is always fun. And this lecture we're going to do almost entirely MATLAB. Okay? So okay, so last time we had looked at the Lorentz system. It's a system with 3 states, and it's a nonlinear system with quadratic nonlinearities. And it's the classical model for chaos in atmospheric systems. Okay? So we all know that the climate is kind of a chaotic dynamical system, and this was one of the first models that exhibited that chaos. And so what we showed yesterday was how to create a right-hand side vector field in Matlab. This function, I have too many of these. This function Lorentz. Okay, so this is a general right-hand side. Y dot equals Lorentz of y would be my nonlinear ODE. And this can take in parameters sigma, beta, rho that I can change at will. Okay. We also coded up our single delta t time step fourth order Runge-Kutta algorithm that we wrote down on the board. And the idea is that for any function you can decide, for any right-hand function of a system of first order ODEs, we can evaluate that function at different points in time and space. And using this Runge-Kutta algorithm, we can get a very accurate prediction for the next state at the next time step. Okay? Any questions about the first two, now that you've had some time to think about them and things to set in? So for example, you could use this RK for single step for your Duffing oscillator problem, right? You could write a function like my Lorentz.m, but you could call it Duffing.m. And you could call Runge-Kutta for single step of your Duffing oscillator. Okay? But this function has to be a function of just time and space. So if you have additional parameters like alpha, beta, gamma, delta, then you're going to have to create a function of t comma y using the function handles. So that at symbol, how many of you feel pretty comfortable with the at symbol function handles? Would anyone like one more example of how to do this? Yeah? A few of you? Okay. Okay, so let's see if I can do this. So Lorentz is a function of 5 variables, right? I give it a time times 0, some state like 1, 1, 1, and then sigma, beta, rho. Okay, and if I give it all 5 numbers, it spits out the Lorentz vector field at those parameters and points in time and space. Okay, but I could say my, let's call it like new Lorentz equals a function of t and y only. Okay, so that's what this at t comma y means. This is, I'm defining on the fly a function of just t and y. Okay? And that function is going to be my original Lorentz function of t and y, but I'm going to lock into place sigma, beta, and rho. Okay, so this is the syntax. I can take a function of multiple variables like Lorentz, and I can lock in some of those variables with real numbers or vectors or whatever they take, and I can thus create a function of just t and y. So this is a wrapper. Okay, we're wrapping the function Lorentz, we're fixing a few of its parameters, and we're getting out a function new Lorentz, which is just a function of t and y. Okay, so new Lorentz I could use directly with my RK4 single step or my ODE 45 because those expect functions just of t comma y. Okay? With this at symbol, you can create functions on the fly really easily. I could say my quadratic equals at x dot squared. And if I say my quadratic of 2, it should give me 4. Okay, so these function handles are really flexible. They allow you to inline define a function. You can wrap a function inline by locking in parameter values and recasting it as different inputs. And so that's what we're doing here. In the Duffing example in the homework, and then in this Lorentz example, we have these 2 variables which are actually going to be changing, like time and space. Those, y is my position that's getting integrated. And then sigma, beta, rho, we're going to lock into place for different examples. Okay, good. So we have Lorentz. We have RK4 single step, which takes in a function of just t and y. And then we have this simulate Lorentz function where we have this big for loop. And for every dt, we step our state forward using this wrapped function we just wrote. This is like my new Lorentz function. Okay? So this is just a rehash of what we did last time. And when you simulate this and compare against I lost my cursor. Oh, this is going to be impossible. Okay, so when you compare that solution with ODE45, you say, okay, RK4 single step versus ODE45. We find that they actually agree very, very well for a little while, but then they start to disagree at the end of the trajectory. At the end of the time interval, these trajectories are actually separating. Okay. So have I already explained what, like, some of the formal definitions of chaos might be? No? Okay, this is a good time to do it. So probably the most practical and formal definition of chaos, this is going to be really practically useful for everyone, is a system is chaotic if its solutions have a very sensitive dependence on the initial condition. So you probably heard this before, sensitive dependence on initial condition. What that means is if I have some initial condition and I perturb it even very slightly, like 0.00001 difference in the initial condition, after some time, they'll agree for a little while, but then after some time, those two solutions will go to very different places, meaning I have a lot of sensitivity, a lot of change due to a very, very small change in initial condition. That's the hallmark of chaos. If a system has that, it is chaotic. If it doesn't, it's not. Okay? That's mostly true. So let's do an example of this. Let's take our So this is a little dangerous. I've never done this demo, but I decided 5 minutes ago that I want to show you what this actually means. So we have Lorenz's parameters, we have our initial condition, and I'm going to define an epsilon as 0.0001 times 1's 3, 1. Okay, so my epsilon is a perturbation to my initial condition, and it's 0.0001 times a column vector of 3 1s. So I'm going to simulate the system with just y, and then I'm also going to simulate the system with y0 plus epsilon. So I'm going to have two initial conditions very close to each other. We're going to start them off, and we're going to see where they go. Okay? And maybe I'm going to make this 0.001 because I've never done this demo before, and I don't know how sensitive it really is. Test sensitivity. Okay, so I wanted to show you how RK4 single step works, how you would actually code this up. But for all, for now, I'm going to use ODE45. Okay, so I have this solution. ODE45 for this initial condition y0. Okay, so if I run this code, it's going to generate one trajectory, this red trajectory, starting at y0 and doing its thing. Now I can take this exact same ODE45 code, say hold on, and instead of giving it an initial condition y0, I'm going to give it y0 plus epsilon. Right? Small perturbation to my initial condition. We're going to see where that trajectory goes. And then I'm going to plot the same stuff, but in blue. And now my legend says y0 plus epsilon. Let's hope this works. Okay. Interesting. So it's almost exactly the same as the other example we showed, right? They start very, very close together. They agree for a long time. But then towards the end of this trajectory, you can see that the blue and the red curves are starting to separate, right? Let's run this for just a tad longer. So instead of time 0 to 4, let's do like 0 to 5. Let's see if I can make this bigger. It's a little hard to see now. Maybe 0 to 10, and let's make this bolder. Okay. So at the end of this simulation, Now, the red and the blue curves are like eventually going to very, very different places, right? They're going to go to completely different sides of this butterfly attractor now. And for all intents and purposes, they're completely different trajectories, even though they started very close to each other. If I wanted to quantify how different their trajectories have become, what could I do? Yeah. Yeah, let's plot one minus the other. That's a good idea. Okay, it's a little tricky because we have a 3 vector, right? So if I plot just the first column of y1, it looks like this. Okay, that's my first component of this trajectory. My second component also looks like that, and my third component is just oscillating. So how am I going to compare all 3 of these in time? I'm going to call this y2. Okay, so how, if I have these, every point in this is a 3 vector. How do I compare all of these 3 vectors? Yeah?
You just calculate the distance between the endpoints for all of them and plot that?
I think so, yeah. So I can just compute like the L2 norm, the Euclidean distance between these 3 vectors for every point in time. Okay, so let's make sure we do this right. Size of y is 1001 by 3. So I'm going to say for I equals 1 to 1001. Diff of I equals norm of y2 I colon minus y I colon, I think. Okay, so 1001 time points, and for every time point I have 3 values, x, y, and z. So what I'm going to do is for every single time point, I'm going to evaluate how close those trajectories are at that point in time, which is the norm of that set of positions at that time minus the other set of positions at that time for the 2 trajectories. So norm is just a nice command that computes the square root of the sum of the squares of x squared plus y squared plus z squared. Okay, it computes the distance. Let's hope this works. And now let's create a new figure. And we're going to plot the diff. Interesting. Okay. So this isn't exactly what I was expecting. That's the fun of doing live demos. This is what the difference looks like in time. Okay? So for a while, they start off agreeing very, very closely. But then pretty quickly, you actually get huge disagreements. And what do these big spikes correspond to, do you think? Anyone? Yeah?
They're on different sides of the butterfly.
Right, they're on different sides of this butterfly attractor. So like at this point, kind of after time, 500 time steps, these things are completely on different trajectories on the butterfly. Sometimes they get close to each other, but then they're completely going to different sides of this attractor. So that's what we're seeing here. This is like full chaos has set in at this point. But let's zoom in down here where they actually agree pretty well. Okay? See if this works at all. Okay. So at the very, 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 very onset of this initial condition perturbation, what we have actually looks a lot like exponential growth. Okay? So this is another hallmark of chaos, is that if when you see 2 trajectories that start really close to each other, in fact, why don't we make this more exaggerated by making our epsilon much smaller. Okay, we're going to start with a smaller perturbation so that they stay closer for longer. We're going to plot the same thing. And now notice they agree for a lot longer, right? And if I zoom in and zoom in and zoom in, actually it looks basically the same. That's interesting. But basically, you have this kind of exponential divergence of these 2 trajectories. So that little epsilon is getting multiplied by e to some lambda t in time, and they're getting farther and farther and farther apart. Okay, so that's the other hallmark of chaos. This kind of quantifies what we mean by high sensitivity. It means that we have exponential divergence of these two trajectories at early time. Okay, and this would be true for any point that I selected. For any initial condition that I chose, I would get an exponential divergence of these initial conditions. Okay. So are there questions at this point? We're going to kind of code up a more sophisticated example, but I just want to answer questions right now. So what are some examples of systems that are a little bit less mathematical that have this sensitivity to initial conditions? So fluid flow is sometimes chaotic. In fact, you can break fluid flow into two broad categories, those that are chaotic and those that are not chaotic. And usually in fluids, we call that laminar and turbulent. Okay, so turbulence is fundamentally a chaotic phenomenon. If you had a turbulent flow and you dropped a little bubble or a piece of dye, and if you move that some tiny, tiny epsilon, those dyes would go to completely different places very, very quickly, and they would diverge exponentially quickly at first. Okay? So fluid flows that are turbulent are chaotic. What are some other examples? Yeah.
Planetary movements with gravity.
Planetary movements with gravity are chaotic in some places. Yeah, they're all chaotic for really long times, so we can't predict where all of the planets will be very accurately for an arbitrarily long time horizon. In fact, one of the most powerful computers in the world, at least a decade ago, was called the Ephemeris. It was a computer that solved a simulation called the Ephemeris, which essentially tracked every planetary body that we knew about, all of the planets and the moons and the space junk and the big comets and all of the stuff that we knew about. And because these objects are really massive and really slow, the chaos, this exponential diversion of trajectories, might take 10,000 years. But in 10,000 years, it's very, very hard to know where everything will be because all of these trajectories are kind of asymptotically diverging from each other based on our uncertainty of how close we know the initial conditions and the masses. Okay? So this is another point I really want to make, is that in any engineering system, we only know the parameters of the model and the initial conditions to some finite precision, right? Like you can only machine something to some real finite precision. You can only measure the initial condition of a planet to some finite precision. And so there's a fundamental uncertainty. There's a fundamental kind of ball of uncertainty in every initial condition and every differential equation that you ever write down. Okay? And so that's why chaos is such a nasty problem, is that it gets, that uncertainty in your initial state of your system gets magnified and stretched and becomes a bigger and bigger problem farther and farther in time. Okay? So there's a whole field called uncertainty quantification that has cropped up to address this problem, and it's huge in mechanical engineering. Like, really, uncertainty quantification has been born out of mechanical engineering, where you have finite precision measurements and initial conditions and manufactured things. What are some other examples? Any other ones? So climate is super chaotic. Yeah, weather is very chaotic. If weather was not chaotic, then we would know what the weather would be 3 months from now. But it's not. So we can only tell what the weather is going to be for a few days. And there's actually uncertainty on those measurements. Like, they get it right maybe 70 or 80% of the time, but there's always uncertainty because we just can't predict. There's too much chaos, and we don't have good enough initial conditions. And it moves quickly. Okay, that's enough examples for now. There's a lot more. Many systems are chaotic, but lots aren't. One of the first examples of chaos was this experiment by a guy named Phil Holmes, who is actually visiting the applied math department at UW right now. He's one of the greatest kind of ODE people still alive today. And he built an experiment with another guy named Moon, where they took a steel beam where you could like strike the beam and you have some elastic equation. Maybe it's like a linear, or if you hit it hard enough, you get some nonlinear elastic deformations. And what they did was they put two big magnets on either side of it. And now when you strike this thing, when it gets close to one magnet, it starts feeling a different set of forces, and then it moves back and forth because it has, its equations of elastic motion. And they actually find that this system, very simple system, is extremely chaotic. You can't predict at all like what the motion of this beam will do when you put those two magnets next to it. So this was, before this experiment that was extremely well measured, people thought that chaos meant you built a shitty experiment. They thought that if you couldn't predict where your solution was going to go, it's because you built in some bad uncertainty, or you messed up your calculations, or your experimental measurements aren't good enough. But they showed that these are, were nearly exact experimental measurements, and the system still had this chaotic behavior. Okay, so for a long time, there was a dispute about whether or not chaos was even real between practicing engineers and mathematicians. And so Phil Holmes, who's visiting the applied math department, was one of the first people that definitively shut down the naysayers and actually proved that chaos was a real thing in physical systems. So you should meet Phil Holmes. He's a great guy. He works on insect locomotion now. He can tell you why cockroaches run even when their legs get ripped off, or if you they actually put jetpacks on cockroaches. They're such good runners. They're so robust that you can mount a little rocket pack to the back of a cockroach while they're running away from something, and you turn this jet on, and they veer over, but within maybe 5 or 6 steps, they actually recorrect and get back on track to where they were going. Like, incredibly robust animals. And Phil Holmes is one of the world's experts on insect locomotion. Okay, so something I want to do here is, there's 2 things I want to do. I want to really get to the bottom of this idea of uncertainty in initial conditions. Okay, and so what we're going to do is, instead of simulating one point through this system, I'm going to create a grid of a bunch of points really tightly together, and we're going to simulate all of them and follow the trajectory of this group of nearby particles. Okay? And I also, so instead of integrating one point, we're integrating like a volume of points. And the other thing I want to do is illustrate why some codes in Matlab are really slow and how you can make them faster. Okay, so a lot of you are going to use Matlab for research, which is great. It's what I use for research. You can prototype things. It's really easy to simulate and visualize and do numerical experiments. But Matlab can be terribly slow. How many of you think you know why Matlab is terribly slow? Why is Matlab terribly slow? Okay, what does that mean?
That means that every time it reads a variable, it says, what variable am I? Like, am I int, am I string? It checks. And it does like dynamic typing and dynamic memory allocation and things.
Right. And every time you write a for loop, it actually essentially compiles that code locally in time to execute it on your computer. Okay? So there's a difference between codes that are compiled ahead of time, like C and C++ and Fortran, and interpreted languages that run kind of as the code is running, it's being compiled, like MATLAB and Python and interpreted languages. Interpreted languages are usually much slower, but also much easier to work with in real time for a human. Okay, so those are the trade-offs. So I'm going to show you the bad, kind of the naive way of doing this volume of particle simulation, and then I'm going to show you the super fast way to do it. Okay. Okay, so I'm going to clear all. I'm going to save this, and I'm going to call it Sim Lorentz Slow. Okay, this is kind of a naive, this is the first thing you would do, but this is the naive way to solve the problem. Okay, I'm going to copy over some of my parameters from before. Okay, so I'm still going to have Lorenz's parameters, but instead of this initial condition, what I'm going to do is I'm going to create a grid of initial conditions, and I'm going to integrate all of them through the system. So initial condition 1 is going to be a large cube of data. So y naught is going to start at 0, 0, 0. Okay. So how many of you know how to get a big mesh of particles? Any commands that do this really, really easily? Okay, good. So there's a really useful command that all of you are going to love now called mesh grid. Okay? So you create an x vector, let's say for minus 20 in increments of 2 to 20. And I'm going to do the same thing with a y vector and a z vector. And then what I can say is x naught, y naught, z naught equals mesh grid of x vector, y vector, z vector. Okay? And what this does is I'm essentially telling Matlab that I want a cube of data given with resolution in the x direction given by the x vector, with resolution in the y direction given by y vector, and with resolution in the z direction given by z vector. So if I run this, now I can say what is the size of x naught? And it's a big 21 by 21 by 21 cube of x positions. Okay? Size y naught is a big 21 by 21 by 21 cube of y positions, and z naught's the same thing. If I actually type x naught, you see that it's this big, these are all of the x positions in order in this cube of x positions. Okay? So I can construct a for loop for I, for j, for k, and I could count through every single position in this cube and get the x, y, and z positions for everything in this cube from minus 20 to 20. Okay? Okay, good. So now we're going to say, okay, so I'm going to create this new data structure of initial conditions. It's going to be this big 4-dimensional monster, yic 1 colon 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 equals x naught. yic 2 colon 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 equals y naught, and yic 3 colon 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 equals z naught. Notice I have to give it 3 colons because x naught is a 3-dimensional array. So that's the only way that it could possibly fit in here. Okay, now let's plot yic 1, yic 2, yic 3 in red dots with line width 2 and marker size 4. Axis. So I'm going through all of these details because I want you to also know how to visualize data. Okay, so you're going to be able to have all of these codes, and now you're going to know how I make plots of data. Shit. Okay, plot 3. Okay, so this is my initial cube of data. I changed the view. View is a command that allows you to rotate your camera view so you can see it from different angles. So that's my initial cube of data. Kind of cool. So axis and view and draw now are just things that make it look nice on the screen. So those are kind of non-technical. Okay, so now we're going to compute our trajectory. We're going to make a dt of 0.01. a duration of 4, a time span from 0 to duration. And the amount of time points we're going to have is duration divided by dt. And my particles are yic. Okay, so now what we're going to do is we're going to step for all of the time steps. We're going to take this cube of particles and we're going to advance it 1 dt forward. Okay? Okay, so for our time step equals 1 to L, the number of time steps. Okay, so to advance this entire cube of data, I'm going to have to write this nested for loop for I equals 1 to blah, for j equals 1 to blah, for k equals 1 to blah. I'm going to have to step through all of the positions in this cube and step each of them forward 1 dt. Okay? Because my RK4 single step and ODE45 only knows how to handle one trajectory at a time. Okay, so my time equals step times dt. For I equals 1 to the length of my x vector. For j equals 1 to the length of my y vector. And for k equals 1 to the length of my z vector. I'm going to say my y in is y particles colon I, j, k. Then I'm going to step these particles forward 1 dt, and I'm going to save them to my trajectory. Okay, so I'm going to do my RK4 single step of my Lorentz function on that particular. So for this particular I, j, and k, I pull that position at that current time, and that's my position, and I'm going to step it 1 dt forward. Okay. So Lorentz t comma y comma sigma beta rho dt time y in. And y particles colon I, j, k equals y out. End. Okay, and then for every single one of these time steps, I'm going to plot my new particles. Okay, so I'm going to do the same plot 3 command. Y particles 1 colon, y particles 2 colon, y particles 3 colon in red dots with the same line width and all of this stuff. And the same position and axis and all of that. Okay, so if I run this, this is a long code. I'm not expecting this to make total sense right now. But when we run this, we're stepping for every dt. We're going for every single little point in this cube of data, and we're stepping them all forward 1 dt, and then we plot them. And then we do it again and again and again. Okay? Let's hope this works. Okay. So we're starting to see the effect of all of these particles as they advance through my Lorentz attractor. Okay? So the simulation has gotten faster since the first time I wrote it because my computer is much faster, but it's still painfully slow to watch. I really want to know where these particles are going, and they're not moving there fast enough for me. Okay? Okay, so are there any ideas for how we could make this much, much faster? Has anyone tried making a Matlab code way faster, like this? Yeah, what do you do?
Find a way to vectorize something without using nested for loops.
Okay, so there's this notion of taking my nested for loops and turning this into a vectored operation, a vectorized operation. So what that means is, so I told you Matlab is interpreted, which means that it kind of reads every line and interprets it as it's going. But it's built on top of really powerful compiled codes that were written in Fortran decades ago. Okay? So matrix multiplication is super duper fast in Matlab because it's calling a compiled code to do matrix multiplication. Taking a singular value decomposition or matrix factorization or like multiplying two matrices is way, way fast. So if we can find some way of taking that cube of data and integrating them all delta t at the same time using matrix operations, this should be hundreds and hundreds of times faster. Okay? So in general, vectorizing will make this way, way faster. Let me see how complicated this code is to do this. Okay, I think we can do this. Okay, so what I'm going to do is create a code called Lorentz 3D. It's going to be basically the exact same as my right-hand side Lorentz, except it's going to evaluate this dy not for a single particle, but for a whole three-dimensional array of particles. It's going to look really weird. There's going to be a lot of colons. This is a big arrayed monster. Dy equals, okay, sigma times y2. This is going to look basically the same as our original Lorentz, except instead of the second position of y, it's going to be y2 comma colon colon colon. It's going to be the second position of y for all of the I, j, and k values in that volume. So that's what colon 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 means, is for all of those three dimensions of my array of particles, I want the second state, the y state. Okay, minus y1 colon colon colon, y1 colon colon colon, dot times rho minus y of 3 colon colon colon. This is not that interesting, but if I can type fast enough, you'll see a pretty cool simulation. Okay. Okay, all I did was just modify my Lorentz code, and anytime I saw a y1, y2, y3, I just put 3 colons in front of it because I want to integrate a three-dimensional array of points. So you can imagine putting an I, a j, and a k in here, and you get a y position for that I, j, k. So you're probably going to want to look at this, after class. Okay, so the same code, except now we're going to call this sim Lorentz fast. We have our sigma beta rho. We have our initial conditions. And now to compute the trajectory. See if I can do this. For step equals 1 to L, we have time equals step. We're going to say y out equals RK4 single step at ty Lorentz 3D of ty sigma beta rho dt time yn. Okay, so this RK4 single step didn't change at all. Except now, instead of giving it just a single position for one of those points in my volume, I'm giving it this huge four-dimensional array of all the points in my volume. Okay, and I can get rid of this horrible nested for loop. And if I didn't make a typo, which is a little worried, this will run. Shit. All right, let's try one more. This should be y out, not y particles. Okay, that's good. It didn't complain in the middle. So this will actually run a lot faster if I remember to suppress my output. This should have been more impressive. Okay, where is my output? Okay, there we go. So notice the difference between the fast vectorized version and the really crummy for loop version. Okay, so this was worth all of the boring typing nonsense. So we can do some neat experiments now that this is fast. Before we do these experiments, are there questions? So this was like way too fast to really follow the details of what I did in Matlab. I want you to go back and look at this because you are going to be wanting to vectorize and make your codes fast, and you should see what I did. The bottom line is the built-in function ODE45 does not handle multiple initial conditions well. Neither does our original RK4 single step. So what we had to do is modify, actually our RK4 single step does handle vectors well, and so we modified our right-hand side so that it can evaluate the right-hand side for thousands of particles all at once and create this massive four-dimensional array of right-hand side dy's. Okay? And then we can write this in a massively vectorized way. Okay, questions about this before we start digging a little deeper into the chaos? Yeah.
You said the ODE45 doesn't really handle the vectors well. Is there a function that's already in Matlab that does?
You might be able to manipulate ODE45 to do something similar to what we did. But I haven't been successful doing that in the past, and it's easier for me to just write my own RK4. So if I want to do a big... So Matlab ODE45 also takes variable time steps. So it has kind of an internal error checker so that if it thinks that its error is getting too large for every little dt, it will cut dt in half. Or if it thinks that it's able to, it'll double its dt and go faster. And that doesn't work well with lots and lots of particles because they each need their own dt. And so ODE45's variable time step doesn't work for multiple trajectories. So the RK4 single step that we wrote is a fixed time step Runge-Kutta algorithm, which is better suited for like running lots of trajectories through simultaneously. You might be able to trick ODE45 into doing it, but this is like pretty straightforward. Okay. So I think I'd rather show you some of the neat things now that we have this fast code. In the next lecture, what we're going to start doing. Notice I started with a huge volume of initial conditions over a really large range, and they kind of spread out and filled this entire butterfly attractor. So what we're going to do next time is we're going to pick a single initial condition, and we're going to create a really, really tight cube of initial conditions around it and see how they stretch and fold with the chaos. But I don't think we have time now, so we'll do that on Monday. And I'll bring another physical demo, like an actual physical experiment that exhibits chaos. Okay? All right, that's all. Have a nice weekend.